This is just a quick reminder that you should feel free to pause the video if you ever feel you want more time to think and write. Hey everybody, welcome to section 5.2, day 1 of exponential functions. Check this out, we've got a table here that's super important. I'm going to start over on this side. So we all know that 2 to the 4th is 16. That means 2 times 2 times 2 times 2. 4 times, 2 times itself 4 times is 16. And check this out, if you go down to 2 to the 3rd, that's only 8. 2 times itself 3 times is 8. And then, of course, 2 squared is 4. 2 times 2 is 4. And the pattern that I'm starting to notice is that if you go from right to left, from the exponent of 4 down to the exponent of 3 down to the exponent of 2, what you end up doing is you end up dividing by 2 each time. And the pattern holds if you keep on going further. 2 to the 1, 2 times itself 1 time is just 2. And then 2 to the 0 is 1. In fact, this is somehow sometimes how I convince students that what 2 to the 0 is. As you can see that it fits the pattern, you keep on dividing by 2. And then if you want to look at negative exponents, you do the same thing. You just keep on dividing by 2. That's what the pattern indicates. Divide by 2, divide by 2, divide by 2 to get more and more negative exponents. So remember the 2 to the positive third was 8, while 2 to the negative third is 1 over 8. 2 to the positive 4 was 16, 2 to the negative 4 is now 1 over 16 because you keep on dividing by 2. And so what I really want to impress upon you and remind you is that negative exponents are related to fractions, very much so. They're related to reciprocals, they're related to change the sign, cross the line, all that stuff from numerator to denominator, denominator to numerator. Anytime you have negative exponents, I want you to remember fractions. So what happens when you put a variable, here's the big question for today, what happens when you put a variable in the exponent? Like this, it's not x squared, it's 2 to the x. 2 to the x. Well, we've chosen some x values, some of them positive, some of them negative. Let's do the positive ones first. 2 squared is 4. 2 to the 1 is 2. 2 to the 0 is 1. And as we just reminded ourselves, 2 to the negative 1 is 1/2. 2 to the negative 2 is 1/4. You plot all those points and you get something like this. It's a curve that starts out very incredibly close to 0. In fact, it gets as close as you want it to 0, to the x-axis as you want. And then all of a sudden, as soon as it gets past the y-axis, it skyrockets up, incredibly steep. And these heights double each time. The heights double from 1 to 2 to 4 to 8 to 16 to 32 to 64. So the slope gets very steep very quickly. That's what it looks like. Let's do the same thing. Instead of 2 to the x, let's do 3 to the x. So you remember that we've got 3 as a base and x as the exponent. So 3 times itself 2 times is 9. 3 times itself 1 time is 3. 3 times itself 0 times, that doesn't even make any sense as a sentence, but we can calculate it that it's 1. 9 divided by 3, divided by 3, divided by 3, divided by 3 each time. And you can see, even though 3 squared is 9, 3 to the negative 2 here is 1 over 9. Remember, negative exponents indicate fractions. If you plot those, they're all right here. You can see same basic shape, it's just steeper here and even closer to the x-axis here. Let's do the same thing, except what if the base is a fraction? So we are raising not 2 to the x, but 1/2 to the x. Well, let's start off with the positive ones first. 1/2 squared. 1/2 squared is 1/4. 1/2 to the first power is just 1/2. Anything to the 0 power is 1. 1/2 to the negative 1. What exactly is that? Well, it turns out that if you want to change the sign, you have to cross the line. This 2 goes up here and the 1 goes down there. You take the reciprocal. 2 over 1 is equal to the positive 1, which is 2. And that makes sense. It fits the pattern here. In order to go in this direction, you have to double. You have to multiply each time by 2. 1/4 times 2 is 1/2, times 2 is 1, times 2 is 2, times 2 is 4. You're moving this direction, and it's multiplied by 2. And this is the same thing that you can calculate right here. 1/2 to the negative 2 is the same thing as its reciprocal, 2/1, to the positive 2. 2 squared is 4. Anyway, these are the same values that we calculated last time. They're just in reverse order. We saw all these fractions appear and these positive and these whole numbers down here. That just means that the graph is it's flipped over the y-axis. It has a horizontal dilation of -1, and that makes sense too, because you can see 1/2 to the x is the same thing as 2 to the negative x. The parent function might be 2 to the x, so this 2 to the negative x has a horizontal dilation by a factor of -1. It's a reflection over the y-axis, as we can see right here. So, an exponential function is the function a to the x, where x is a real number, a is greater than 0. We're not looking at any negative bases, only positives. And then a is not equal to 1. That's an exponential function of base a. Here's some properties of exponential functions. You can see we graphed 2 of these just on the last page. We graphed 2 to the x and 3 to the x. We hear some more. 1.8 to the x, 2.5 to the x, 4 to the x. One more thing I want to say, not about this graph actually, is that just sodium is the 11th element on the periodic table. That's right, you heard it correctly, sodium. And then you saw that we graphed one of these before. That was 1/2 to the x. But here's 3 more. This is 0.25 to the x, 0.4 to the x, and 0.7 to the x. What do they all have in common? Well, you can see the function is written like this, a to the x, where a is some positive number, and it's not 1. It's continuous, meaning you can just draw it. It's not like a piecewise function where you have to draw different pieces and pick up your pencil to put them in different places. No, you can technically just, with one curve, just draw the whole thing. It is 1-to-1. It's increasing the entire time or decreasing the entire time. The domain is -infinity to positive infinity here, and the range is only positive numbers, 0, infinity. For these parent functions, there are no negative output values, and it's never equal to 0. It's going to be increasing if a is greater than 1. So if the base that we have is anywhere, all these numbers are greater than 1, and then all of these numbers are going to be less than 1, 0.4, 0.25, 0.7. These are all going to be decreasing. So you know it's decreasing if a is less than 1. All of these are going to have a horizontal asymptote at y equals 0, and they're going to have a y-intercept at 0, 1. That's because for any value here, if the input is 0, then a to the 0 is always going to equal to positive 1. They all intersect at this point right here. Let's see what happens if we have a transformation. If this is our parent function, y equals 2 to the x, then what happens if we have 2 to the x minus 2? Well, in comparison, the difference between these two is the -2 on the x. You take x and subtract 2. So it's going to be a horizontal shift of +2, because remember, we expect the value to be right here. And x minus what? It's x minus a positive 2. Here, b, the parent function was 2 to the x, so then this is 2 to the x and then -4, because you're subtracting 4 after taking the exponents. It's a vertical shift of -4. Here's a complicated one. There's actually 3 transformations going on. So if you rewrite this algebraically, you break up the subtraction and make it plus, so +5 and then times a -1 here. You can see that you've got a -1 out in front and a +5. And then even if you take this 1/2 and rewrite it as 2 to the negative x, then you'll see that there's a -1 right here. Remember, we're taking reciprocals, and therefore you can make the exponent negative. This is probably the most difficult conceptual jump to make right here. Anyway, we've got 3 different operations going on. +5 on the outside, times -1 on the outside, and times -1 on the inside. So that means each of those three operations correspond to the three transformations. We've got a vertical shift of plus 5. I don't know why it says plus 4. This should be a 5. A vertical shift of plus 5, a vertical dilation of -1. You can see this is -1 right here, and then a horizontal dilation of -1. It's going to be flipped over the y-axis horizontally and over the x-axis vertically. So let's take a look at the actual graphs. I'm just going to graph actually just part A, the horizontal shift of plus 2. So you can see here in comparison, this is the normal graph that the parent graph that we did earlier, 1/4, 1/2, 1, 2, 4. But you can see all these numbers get shifted to the right on the graph. 1 used to be the input to 0, but now it got shifted 2 units to the right. Now, if the input is 2, the output is 1. If the input is 1, the output is 1/2. You see that used to be here at -1. I want you to figure out what the value is right here. You can do that by either continuing the pattern, or you can calculate what is 2 to the -4th. Either way, there's one specific number right there, and I want you to find it. Anyway, if you plot these, then you can see all of these values got shifted plus 2 to the right from the parent graph. So I'd like you to start assignment 5B1. I'd like you to copy the problem list and do the first problem, and I'll see you in class.